Okay, so for today, we're going to start out with some Newton's second law questions that are kind of what we did yesterday, just to kind of refresh our memory. So some elevator stuff, some simple, maybe simple systems questions, but probably not. Okay, we're just going to kind of refresh what we were doing, and then I'm going to move on to showing you some vector-related Newton's second law questions, okay? Namely, inclined planes, okay? Because the inclined plane, the ramp, is the simplest machine, okay? But it is also a great example of Newton's second law using vectors, okay? So we'll be heading on to inclined planes probably in the 20 minutes to a half an hour, okay? What I want you working on right now, because there's a couple of really good questions in here, okay, are questions 10 to 14. Okay, you have a couple of elevator questions in there. Okay, so pay close attention to those. Okay, we know how to do those, right? But 10 to 14 for right now. Okay, and there'll be a couple there that we'll go over as a class. So on 19, we have essentially the setup that we're going to use for our lab on Newton's second law. We're going to have a pulley attached to a cart that is on a horizontal frictionless surface, okay, and we're going to have a mass hanging over the pulley. So what we essentially have then is a box attached to a rope, okay, which is strung over a pulley that is connected to yet another box. Right, so this is the 1.0 kilogram box, and this is the 1.5 kilogram box. Okay, is this a system? It is. It has more than one box. Pulleys are always involved in systems. Okay, and what is the only force causing it to accelerate? Gravity. Which box is gravity acting on? Well, technically it's acting on both, right? But it's only causing an acceleration because it's acting on the 1.5, right? It's balanced out by normal force here for the 1 kilogram box. Okay, so I've got a force of gravity here, m times g, so 1.5, okay, 14.715 newtons. Okay, since there are no other forces, can I do vector sum of all forces in my head? Is that number the vector sum of all forces? It has to be. It's the only force. Okay, so it's the net force by default. There's no friction. Okay, it says horizontal frictionless surface. There are no other forces in this question, so that's my net force. All right, how would I calculate the acceleration of the box? Of the one, it's referring to the 1 kilogram box here. How do I calculate the acceleration?
Force divided by mass of the system.
Right, F net divided by, very important, mass of the system. Right, that's going to mean 14.715 divided by 2.5 kilograms. All that mass is being accelerated by that force. Okay, so when I do that, I should get the 5.9 meters per second squared. But what's missing from this answer? It asked about the 1 kilogram box. What should I put on here? To the right, or forwards, or towards the pulley, or some vector that makes sense for that question. They really didn't tell me any vectors other than this is the setup. If they were asking about the 1.5, I would say the vector is down. Okay, if they said, what's the acceleration of the system? I would just say 5.9 meters per second squared. I wouldn't be able to give a vector because their parts of the system are going different ways. Okay, is that ringing a bell for everybody? Okay, if that's ringing a bell, then Okay, so it's a system question. We are wanting to calculate the acceleration of the system, given that the mass of pail B is 8 kilograms, pail C is 6 kilograms, and the tire is 20 kilograms. Okay, we want to calculate the acceleration of the system. That's nice, they didn't ask you for one particular part. So what do you not need on your answer?
Direction.
Yeah, you don't put a direction, you can't. It asks for the acceleration of the system. One of those pails is gonna move up, one of them's gonna move down, the tire's gonna move sideways. All right, give you a few minutes on that one, we'll walk through it. So for this question here, okay, we need to identify our forces. First, it tells us that they are light ropes. That means they have no mass, which we know is physically impossible, but we're just gonna say that. Otherwise, we'd have to add the mass of the ropes to the mass of the system. Okay, so we're gonna say that they're, these imaginary massless ropes. Okay, and it's on a horizontal frictionless surface, so there's no friction on the tire or the pulleys. That means the only two forces that are acting in this system are the force of gravity on pail C, okay, which is going to be 58.86, 6 times 9.81, and the force of gravity on pail B, okay, which is going to be 78.48. Yeah. Newtons. Okay, can I simplify my free body diagram? What should I simplify it to? Yeah, I should simplify it first to this. And what number should I write in the box?
Mass of the system.
The mass of the system, which is 34 kilograms. Okay, because we got 6 plus 20 plus 8. Okay, so that's 34 kilograms. Now, that system is being pulled this direction by 58.86 newtons, and this direction here by 78.48 newtons. Okay, which is going to mean when we calculate our net force, we're going to do the vector sum of all forces. 78.48 minus 58.86 is 19.62 newtons, if my math is right. Okay.
On the test, could I just do 8 minus 6 times gravity?
Please don't.
Okay.
It would work for this question, but I worry about doing that, like getting in a habit of that when some of the forces aren't gravity, right? Because if I've got a force that's not gravity acting on a mass and I get in the habit of doing that, I might multiply it by the wrong acceleration. Okay, okay, so I've got a net force of 19.62 newtons this way. The vector's not going to matter, we already said, because we're actually calculating the acceleration of the system. Okay, acceleration of the system. So acceleration will be F net, okay, divided by m, right? And so that's going to be 19.62 divided by 34 kilograms. And it's going to be like 1 point something. No, sorry, not 1 point something. 19.62 divided by 34. 0.58. We have two significant digits there. All right, and I can't put a vector on that because that's the acceleration of the system. Is everybody okay with the system questions? Okay. Okay, so it's our first type of vector question. It's also our first static example. Okay, so I'm going to ask you an English question. What does static mean? Stays the same, right? Or unchanging, okay, or something like that. All right. So this is a static condition example. So let me ask you this. Got this roll of tape suspended from my hand by a string. It's hanging, would you agree? What's the net force in this situation? Right, why is it 0? There's no acceleration, it's not moving, there's no acceleration. Okay? In a static example, the object's not moving. That means there's no acceleration, and thus that means the vector sum of all the forces is 0. Okay? That's what we have to understand about this situation. In this situation, they said the sign is hanging from two different buildings. Right? Hanging does not mean falling. Hanging does not mean being lifted. It means it is suspended. Okay? Suspended means it isn't moving. All right? So cable 1 is angled 55 degrees below the horizontal from one wall, and cable 2 is horizontal and attached to a different wall. All right, so I gotta kind of visualize this. I'm gonna make this my sign, and these are gonna be my two walls. Okay, it's suspended between these two walls. And it says the first cable is 55 degrees below the horizontal. Okay, so that's 55 degrees below the horizontal. Okay, and I'll call that cable 1. Okay, and it says cable 2 is horizontal and attached to a different wall. Okay, and the store sign is 35 kilograms. Okay, is everybody all right with that situation the way I've drawn it? It seems to be what the question said, right? One cable is angled and the other cable is horizontal. Okay? The combination of the forces of those two cables is keeping the sign from falling. Why do I need those two cables in the first place? What would make it fall? Don't overthink this, guys. What makes anything fall? Gravity. Is gravity another force in this question? Which way does gravity act? Down. Okay, can I calculate the force of gravity? All right, I know the mass. Okay, mass times gravity. All right, so we got 343.35. Okay, sign's not moving, so that means there has to be an upward force of 343 newtons. Would you agree? Which cable can provide that? 1 or 2? Because there's one of those cables that cannot act against that force. Has to be cable 1. Why can cable 2 not help resist gravity? Because it's horizontal. It has no component acting vertically. Therefore, it cannot oppose a vertical force. Okay? What is cable 2 doing? It's pulling to the... Why does it need to do that? So it doesn't swing, because cable 1 is pulling at an angle. That means that cable 1 actually has a vertical component and a horizontal component. Its horizontal component goes to the left, which means that is opposing cable 2. Would you agree? That's the reason I have cable 2. Without cable 2, okay, as Addie said, that sign would swing into the other wall. I need that cable there to act against the horizontal component of A. The vertical component of A is the part that's offsetting what? Gravity, because it's the only vertical force upwards that I have in the whole question. All right, so that tells me then that I know this one. Now the question wants me to find out how hard cable 2 is pulling. Can I find that now? Well, it seems to me that I've got a vertical force and I've got a triangle that it's part of. I might just do this because that would allow me to use the 55-degree angle that I have over here. Okay, so now that I've got that 55-degree angle, if I find this horizontal component here, that's going to be equal but opposite to cable B, or cable 2, sorry. Would you agree? Okay, so if I'm looking at this, I got to do a little bit of trig here. I've got this angle, I've got the opposite side, and I'm looking for the adjacent side. So what trig function am I going to use? Tan. So, right, so the tan of theta is going to equal the opposite side, which is what I have, 343.35, divided by the adjacent side, which is what I'm looking for. Right? So if I cross multiply here, what I'm going to have is that cable 2 is going to equal 343.35 divided by the tan of 55. Oh shoot, I pressed that button again. How are we going to fix that? Okay, divided by 10 of 55. Okay, so according to my calculator, cable 2 is pulling to the right with 2.4 times 10 to the 2 newtons worth of force. 240 newtons. Oh, sorry. I actually, according to the way that question is written, I wouldn't have to write right. Because it actually asks for the tension. And tension pulls both ways. If it asked, how hard is cable 2 pulling on the sign, then I would have to say to the right. But if it asks for tension, tension is just how tight's the cable. Okay? That doesn't have a vector because cables pull in 2 directions at the same time. Okay, weird one. Okay. How much math did I have to do for that? 2 calculations. I calculated force of gravity, and then I did a trigonometry calculation. Was that tricky in my head, though? Was there a lot of thinking and force identification and figuring and all that kind of stuff? A lot. Okay? That's another prime example of a question. It's probably only a 4-mark question. Okay? But it's tricky, because there's just not that much to it other than being able to visualize the situation. Okay? And when we start getting into vectored forces like this, it gets even crazier. Okay? It's tough enough when they're all collinear, right? But when we start getting into forces that are vectored, okay, we really have to look into the situation a lot. Okay, try that system question. Friction's involved now. All the ones we did were frictionless. Okay, now we got friction involved. Okay, so the friction on the table, this is the table here, okay, is 32 newtons. I want the acceleration of the 5 kilogram mass. All right, so if the friction is on the table, friction is only acting on which box? The 4 kilogram mass. Directly. I mean, it's acting on the system, obviously, okay, but it's only directly acting on the 4 kilogram box. So it's 32 newtons that way. Friction, by the way, always opposes. Okay, so if you know the box is moving to the right, friction's going to the left. Always opposes. And it's always holding you back and working against you. Okay. And then we have the 5 kilogram mass. That is the one where the driving force is acting, and that driving force is the force of gravity. M times G is 49.05 newtons. Okay, those are my only 2 forces. If I'm not told otherwise, I assume my rope is massless and my pulley is frictionless. Okay, so I can just make those assumptions unless I'm told otherwise. Okay. Now, I need to find the acceleration of the 5 kilogram mass. Do I actually ever use the 5 by itself other than what I did there? No. If I want to calculate the acceleration of the 5 kilogram mass, I find the acceleration of the system. All right. So first thing I need to find is the net force acting on the system. That'll be 49.05 minus 32. Because what I really have here is 9 kilograms worth of mass being pulled this way by 49.05 and resisted by 32. Okay, that's really what's going on here. So 49.05 minus 32 should give me 17.05, right? Okay, now that I've got the net force, I can calculate the acceleration, F net over m, 17.05 over 9 kilograms. Okay. So 1.9, actually we only have one significant digit in there, don't we? So 2. 2 meters per second squared down. It asked about the 5 kilogram mass. That's the way the 5 kilogram mass is going. Okay? All right, questions on the system question there?